everyone. Today I want to talk about one technical part in paper incremental learning for robust visual tracking. And since I don't have enough time recently, so I'm not sure my understanding is 100% correct. So we can discuss if you have some questions or concerns in the following slide. And before we're talking about incremental SVD, which is one of the major proposals in this paper, and we want to have a brief introduction of a general tracking method. Actually, for a general approach of a tracking object, and we are mainly concerned about two parts. First one, we want to design a dynamic motions object. For example, if you want to tracking a human or vehicle, you may need a motion like with a velocity or something. And for the most easiest situation, you can consider other case, for example, like random motion. And so we can use a Gaussian distribution here. And another one is if we want to calculate the similarity about the different partitions in next frame between the current frame, and we need appearance model of object. And today we are focused on the number 2 model, which is object appearance model. And there's a problem in practical applications. Even for rigid object, actually, for example, if you're tracking a vehicle from different view, the appearance model may be not exactly occurred in the training data. So the problem is in a processing tracking, when we have new data, so what can we do about new data? And that is the motion of the incremental SVD algorithm. And in this paper, actually, we restrict ourselves of the representation of object, that means appearance model, using Eigen basis tracking. And it also faces the same problem. That means for in offline training, we have Eigen basis, but when in the process of tracking, we have new object. So we would like to combine new data into our Eigen basis. And that means we want to update the Eigen basis if we have new data. And so the first one, I want to give a brief introduction of Eigen basis. And because on this document, if I cannot make it clear, later I will write on the whiteboard to discuss. For I write over there. And we have the training data. It's generally size maybe m, and number of training data maybe n. And every column is an image. We transfer the 2-dimensional image to a 1-dimensional vector. And we would like to project this matrix into some basis vector. And because if we consider we are more care about the vector, so we want to reduce the dimension of this n to a smaller number. Generally, it's much smaller. And so also after this matrix reduction, we would like to keep more information, more important information. And so we have this A, and the covariance matrix A transpose. And because we care about this low vector, and if you care about this column vector, you can calculate A transpose A. But in our case, we will calculate A transpose. That means in this covariance matrix, by the way, for the simplicity, we just consider the zero mean case. like for example, we think we already subtract the mean value from every column, and we want to calculate this covariance for this covariance matrix, and we would like to find some eigenvectors, and this is eigenvalue, and this eigenvector's inverse. Since this matrix is symmetric, so this turns to from inverse to transpose, and that means from the original training data A, we have this covariance matrix AA transpose, and from AA transpose we have these eigenvectors, and for our purpose, we would like to reduce the n dimension to some small number from capital N to N. That means for this eigenvectors matrix, we can simply keep the largest small n number of vectors. This is principal component. And when we calculate about this eigenbasis, actually we're using singular value decomposition. Because in here, and for this covariance matrix, we want to calculate the eigenvectors, and by singular value decomposition, we have A, we have this is called light singular vectors, and we have this is sigma, and this is A transpose. And so compare this one to the covariance matrix of decomposition. Actually, we can make some steps to disappear the right singular vectors. And similarly, we calculate this one. It will equals to transpose B sigma mu. And in here, this mu is also some. This is not eigenvector, because for the singular value, we will consider mu and multiply mu1 will equals to something v1. And this mu1 is in column space and v1 is in row space. So this is not definition of eigenvectors. But if we calculate A times A transpose, then V transpose V will disappear, and it turns out to mu sigma since this is diagonal matrix, so and so compare this SVD and the purpose of DC, we find we can using SVD to get the eigenvectors of a covariance matrix, and we just simply keep the largest eigenvectors. This is the eigenbasis in this step. So in summary, we have a trailing image. This is M by capital N, and we get some eigenbasis by smaller. For example, we have like 2,000 or 3,000 trailing image. So finally, we have this eigenbasis like 10 or 20 is much smaller number. And so this is an example. We use using a fixed trailing image, we get this fixed eigenbasis. I didn't calculate this; it's just from other people's PowerPoint. And so here's our problem. That means, right? Again, our problem occurs. data B, and we would like to have update eigenbasis about AB. And for some straightforward idea, we can simply use SVD for this new matrix. We can calculate this. But the idea of the point of this method is we don't want to recalculate everything. We want to see is there any some easier or less complex method to acquire the new eigenbasis. And so the data is just new data. So in summary, we have old data. This M by N. We have new data. M by maybe K. And K is much small. So generally, maybe only one image, one or something. We use K. And we have a new combined matrix. A, B. It's just the same number of rows but number of columns and added by K. And we want to calculate SVD, the A star, U star, sigma star, A star, transpose. And we want to calculate this one. And actually, there's one point we should mention. Since in offline we already calculate the principal components analysis, that means for the original A, we don't need to use this one because A, we can, for example, mu sigma V transpose. This is M by N, and we can get this M by M, and this M by N, this M by N. Since we just keep the largest small n number of vectors, so actually this turns into we only keep M by N columns, and this is N by N, and this is also N by N. That means even though I write whole data set is A, but actually this number is smaller. And we don't use the original training data. We want to, this means this is the original training data projection on the new databases, and we only keep the largest n eigenbasis vector. That means for the number of columns, I use small n but not capital. And we should keep in mind that M should generally M is much greater than N, and generally N is also greater than K. So this is so back to our purpose. That means we want to calculate the singular value decomposition of new combined matrix, but we don't want to directly calculate everything. And so the steps of partitioned singular value decomposition is we have new data B. So the first of all, we will using also normal decomposition, and we use this mu B, and using some also normal decomposition, and we can have mu and J. This mu, this is also normal, and G is also normal, and times something. And maybe we can use some ordinary method. And so this is, we already know this, and the first step is we get the also normal basis of G, And the second steps, so this is our combined matrix. We want to calculate the singular value decomposition of this matrix. So the next step, we just they decompose this matrix something like this, and this is mu j, and this is also normal matrix, and it's sigma, and so it's kind of a decomposition of B. So this is mu transpose B, and for this J is G transpose B, and 0, well, times, and this is V 0, and first of all, they decompose this new combined matrix into something like this, and we will verify whether the multiplication of these three parts is AB. So for the right hand side, and this one will be mu sigma, and for this column will be mu transpose B J transpose B, and for the third component is since we have a transpose, so this is if we want this transpose transpose this is just a dynamic matrix, so we can check it like this. So just keep in mind that this A matrix, this is just a singular value decomposition of A. We already did this on the offline. And this one, this is also normal. This is anyone is also normal vector. This is also, and so mu transpose B is just the B on the vector mu's projection. This is also on the vector J's projection. So the combined these two steps is just a B. That means AB can be decomposed into
2B.
No, yeah, it's 2B, but actually it's this is I, this is I.
It's not actually like U is not square matrix. U is not exactly of normal.
U is no also.
I mean U transpose U is identity, but U transpose is not identity. It's not a square matrix. U and J is not a square matrix.
Yeah,
it's not a square matrix. How can you be like? I mean, it's not an orthonormal matrix, but the columns are orthonormal. What you said is right, but you got confused. But it's a projection actually. You project to two different spaces, and it's kind of the two spaces are orthogonal. So when they combine together, you get back B.
2B? I don't think 2B.
No, it's not 2B. It's right. Yeah.
Yes, we can consider as like mu G is totally is orthonormal matrix. And so that means the combined matrix can be decomposed into these three parts. And for the first part, this is also normal matrix. For the third part, it is also normal. But for the second part, it's not exactly diagonal. That means this is the complexity shown here. For matrix and middle, we can define some in the form of this, and we will calculate SVD of middle of this one, and because we already have G is not as complex as the original matrix because that's huge, and we also already have. That means we only need to calculate the doing the SVD of the middle matrix, and the middle matrix the size is this is by n, and ut this is by n by k. There's no number. This is okay. That means this matrix size is n plus k and n plus k, and that means we transfer our purpose to SVD of a bigger matrix to SVD of smaller matrix, and for the complexity, I didn't get the detail of the conclusion of in some books we said for a matrix of n by n, the fattest calculation will be proportional to k1 mx squared plus k2 Q, something like this. So A star is our original matrix. We want to calculate the last line. That matrix is the smaller matrix, and we can find operations is different. But keep in mind that the m is much greater than n, and n is also greater than k. So actually, in the real application, for example, like phase tracking or some vehicle tracking, and it's a huge state of complexity, reduction complexity. So that is the main point of actually that paper including also other parts. This is just one part of technical proposal in that paper. That's all.
You explain this part. Explain this.
Pardon?
This part. Can you explain it more?
Okay. And our original purpose is we want to calculate SVD A star. This size is like because A star is A B, so it's kind of m plus k. So we want to calculate SVD of this matrix, and but finally after this algorithm, now we can transfer to calculate SVD of another middle matrix, and this matrix size is only n plus k plus k, and this n is like size of image. N is number of eigenbases, and k is a new number of new data, maybe 1 or 2. But size of image we transfer to 2-dimensional to 1-dimensional, like even a 20 by 20 is 400, for example, 400. And number of eigenbases maybe 10 or 20. And for in some document, actually, for calculation of singular value decomposition, the best complexity we can get is for m by n matrix, that will be k1 mn squared plus k2 cube. Something like this. If we cover our original purpose to calculate a much greater size matrix with much greater size and into a matrix with a smaller size, and based on this complexity, we can save a lot of the operations. That is the point of the last slide. Simply put, we want to singular value decomposition of a matrix, but the original matrix is larger, but after some this decomposition, we can transfer to decomposition of a much smaller matrix.
What's K1 and K2?
That book said K1 is 4, K2 is like 22, but I didn't review any detail. Any questions?